So far, we have explored inelastic collisions in 1 and 2 dimensions. In this video, we will integrate inelastic collisions with all the other concepts we have seen in this course. A classic question that combines momentum and kinematics is one where an astronaut is stranded and has to get back to their spacecraft. Consider this example. An 80-kilogram astronaut is stranded 5 meters away from the airlock of his spacecraft. He throws a 3-kilogram ball away from the spacecraft. How long does it take him to reach the airlock? In this question, we were told that the astronaut holds a ball and is otherwise immobile in space. So this is photo 1. The astronaut throws the ball, and as you probably guessed, that will cause them to move backwards. That's going to be photo 2. Until such time, that is, as the astronaut actually reaches the airlock. That would be photo 3. By the way, this maneuver was actually used in one of my favorite episodes of Doctor Who, so extra credit to anyone who can find out which episode that was. So, we have been told that the mass of the astronaut is 80. The mass of the ball is 3 kilograms. The distance from the astronaut to the airlock is 5 meters. And we have to figure out how long it's going to take for the astronaut to reach the airlock. So photo 1 is before he throws the ball. Photo 2 is a nanosecond after the astronaut throws the ball. And photo 3 is when the astronaut arrives at the airlock. Photo 1 to photo 2 has to be solved using conservation of momentum. And photo 2 to photo 3 has to be solved using kinematics, specifically one-dimensional kinematics. I'm going to set my origin at the starting point of the astronaut. I'm going to set rightwards as being positive. Now, let's plug in all of the information that we know into conservation of momentum. The mass of the ball in photo 1 times the velocity of the ball in photo 1 plus mass of the astronaut in photo 1 times the velocity of the astronaut in photo 1 is equal to mass of the ball in photo 2 times velocity of the ball in photo 2 plus mass of the astronaut in photo 2 times velocity of the astronaut in photo 2. So this is conservation of momentum. Remember that conservation of momentum really says that the momentum of each object, in this case, momentum of the ball plus momentum of the astronaut in photo 1 must be equal to momentum of the ball plus momentum of the astronaut in photo 2. And when we expand that out, we get this expression or this equation over here. So this step, going from conservation of momentum to the expanded form, should be familiar if you have seen the last 2 videos. If this looks, or if you feel hazy about this step, please check out those videos or ask me about it. Now, let us substitute in all of the information that is known. We were told that the mass of the ball was 3, the initial velocity of the ball was 0, plus mass of the astronaut, 80, plus velocity of, or times velocity of the astronaut, 0, is equal to mass of the ball, 3. The astronaut threw the ball at 10 meters per second. But since that's leftward, we have to count that as being negative 10 I hat. Plus mass of the astronaut, 80, times the final velocity of the astronaut, which is unknown. Let's start simplifying this. 3 times 0 is 0, plus 80 times 0 is 0, is equal to 3 times negative 10 I hat is negative 30 I hat, plus 80 times VA2. Simplify still further by moving this 30 to the other side. 30 I hat equals 80 times velocity of the astronaut, 2. So the last step is just going to be to divide 30 by 80 to find out the velocity of the astronaut, 0.375 meters per second. So the velocity of the astronaut in photo 2 is equal to 0.375 I hat meters per second. So now we have used conservation of momentum to figure out the velocity of this astronaut going backwards. The next step is to apply the principles of kinematics, 1D kinematics, to figure out how long it takes for the astronaut to actually reach the airlock. So let's write down everything that we know between photo 2 and photo 3, from the nanosecond after he threw the ball to just as he is reaching the airlock. So delta x is 5 meters. The initial velocity of the astronaut was 0.375 I hat. The final velocity is not known. Because the astronaut is in space, there is no further force acting on him after he has thrown the ball. Therefore, the acceleration of the astronaut must be 0 because there are no further forces acting on him. And the time is also unknown. So, time is unknown, but initial velocity, delta x, and acceleration are known. So we can use toolbox equation number 2 to solve for all of this. So delta x is 5 is equal to v initial, 0.375, times time, plus 1/2 times acceleration, 0, times time squared. This entire term cancels out, and we're left with 5 is equal to 0.35 times t. So 5 divided by 0.375 gives us 13.33. So the time is 13.33 seconds. That is how long it will take the astronaut to return to the airlock. This kinematic section was done specifically from photo 2 to photo 3, and conservation of momentum was done specifically between photo 1 and photo 2. We can combine momentum with two-dimensional kinematics as well. A typical example is a firework that explodes in mid-flight. Consider this example. A 3-kilogram firework is launched at an angle. At its peak, it is 10 meters off the ground and has a velocity of 5 meters per second rightward. The firework then breaks into a 1-kilogram fragment and a 2-kilogram fragment. The 1-kilogram fragment flies leftward at 6 meters per second. Where does the 2-kilogram fragment land? In this question, a 3-kilogram firework is launched from off the ground, and it eventually reaches the peak. When it is at the peak, it is traveling with a velocity of 5 meters per second in this direction. Then it explodes into a 1-kilogram fragment, which is moving at 6 meters per second in the opposite direction, and a 2-kilogram fragment that is moving in the first direction, but we don't know what its velocity is. Eventually, that 2-kilogram fragment is going to land. I'm going to set photo 1 as being the peak before the explosion took place, photo 2 as a nanosecond after the explosion, and photo 3 as the point of landing. I'm going to set my axes like so. I'm going to set downwards as being positive y and rightwards as being positive x, with the origin being on the ground right under where the explosion took place. The last piece of information we were told was that the height of this object when the explosion took place was 10 meters. Now that we have all that information, let us solve for how far this object must have moved after the explosion, how far the 2 kilogram fragment moved after the explosion. So, let's look at photo 1 to photo 2. From photo 1 to photo 2, we can say that the total momentum before the explosion equals the total momentum after the explosion. Let's expand this out. The momentum of the 3 kilogram fragment in photo 1 must be equal to the momentum of the 1 kilogram fragment in photo 2 plus the momentum of the 2 kilogram fragment in photo 2. Expand it out still further. The mass of the 3 kilogram fragment in photo 1 times the velocity of the 3 kilogram fragment in photo 1 is equal to mass of the 1 kilogram fragment in 2, velocity of the 1 kilogram fragment in 2, plus mass of the 2 kilogram fragment in 2, velocity of the 2 kilogram fragment in 2. Now let's plug in everything that we know. The mass of the 3 kilogram fragment, 3. Velocity of the 3 kilogram fragment, 5, and the way that I've set up my axes, this would be in the positive x direction, so that's 5 I hat, is equal to mass of the 1 kilogram object, 1, velocity of the 1 kilogram object, 6 meters per second leftwards is actually negative 6 I hat, plus mass of the 2 kilogram fragment times velocity of the 2 kilogram fragment in photo 2. Now, let's simplify this. 3 times 5, 15 I hat, equals negative 6 I hat plus 2 times the velocity of the 2 kilogram fragment at photo 2. Add 6i to both sides. 21 I hat equals 2 velocity of the second fragment in photo 2. And finally, we divide by 2 on both sides to get velocity of the second fragment in photo 2 is 21 divided by 2 is equal to 10.5 I hat meters per second. So this is now the velocity of fragment 2 immediately after the explosion took place. Now let's use that information as part of a kinematics puzzle to figure out where this object is going to land. I'm going to draw a dividing line over here. And we're going to look at the kinematics aspect over here. So from photo 2 to photo 3, we can set up one of our familiar tables. X, Y, displacement, initial velocity, final velocity, acceleration, time. So the initial velocity of the 10 kilogram fragment was 10.5 I hat. And since it did not have any motion in the y direction, that would be 0 over here. The 2 kilogram fragment is going to fall by 10 meters, but since I set downwards as positive, that corresponds to a positive displacement. The acceleration in x is 0. The acceleration in y is 9.81, again, since downwards is positive. we have three pieces of information in y. We can solve for the time, and then we can solve for the displacement in x. So the time and the displacement are what we are going to solve for. Let's start in the y direction. In the y direction, we know displacement, initial velocity, and acceleration. We can solve for time. There's only one equation that weaves together all four of these quantities, and that's toolbox equation 2. So that would say that delta y is equal to v initial times t plus 1/2 acceleration times t squared. Plug in everything that we know. Delta y, 10, is equal to v initial, 0, times time, plus 1/2 acceleration, 9.81, times time squared. Let's start simplifying this. This term is going to go away, and half of 9.81 is 4.905 t squared. So now we just need to solve for t. 10 divided by 4.905 gives us 2.038, and the square root of that is 1.43 seconds. Okay, now what about the x direction? In the x direction, the displacement is the unknown, but we know the time, the acceleration, and the initial velocity. So we can use all this information, again using toolbox equation number 2, to solve for delta x. V initial times t plus 1/2 acceleration times t squared. So delta x is the unknown, but v initial was 10.5 times time, which was 1.43, plus half times acceleration, 0, times t squared, which we don't really need to bother about because this entire term is going to go away. So 10.5 multiplied by 1.43 gives us 14.99. So delta x is 14.99 I hat meters. That is the displacement of this 2 kilogram fragment as it travels rightwards, and just before it hits the ground. It travels 14.99 meters in the rightward direction. Next, let's look at momentum plus forces. An example here would be a person catching a ball and being propelled backwards until friction brings them to a stop. Consider this example. A 5 kilogram ball is launched horizontally at 10 meters per second. A 70 kilogram man catches it and is pushed backward by the impact. The coefficient of kinetic friction between the man and the ground is 0.15. How long does it take for the man to come to a stop? In this question, we have a ball which is initially in motion and a person who is going to catch it. This person does catch the ball and is driven backwards for their trouble, until finally they come to rest. I'm going to call photo 1 a photo that was taken before the ball was caught. Photo 2 is a nanosecond after the ball was caught, and photo 3 when this character comes to a stop. Between photo 1 and photo 2, we have an inelastic collision, so this needs to be solved using conservation of momentum. So, of course, before we can actually solve any of this, we need to put in all of the information. The ball has a mass of 5 kilograms. The person has a mass of 70 kilograms. The ball is initially moving at 10 meters per second, and the coefficient of kinetic friction is 0.15. I'm going to set my axes like so. I'm going to set my origin to be the position of the person just when they catch the ball, and I'm going to set rightwards as positive. So, photo 1 to photo 2. The total momentum of photo 1 equals the total momentum in photo 2. Let us expand this information out. The momentum of the ball in photo 1 plus the momentum of the person in photo 1 is equal to the momentum of the ball in photo 2 plus the momentum of the person in photo 2. Expand this out still further. The mass of the ball in photo 1 times the velocity of the ball in photo 1 plus the mass of the person in photo 1 times the velocity of the person in photo 1 is all equal to the mass of the ball in photo 2 times the velocity of the ball in photo 2 plus the mass of the person in photo 2 times the velocity of the person in photo 2. Now we're ready to substitute in all of the information that we know. The mass of the ball in photo 1 is 5. The velocity of the ball is 10 I hat, because that's the way we drew our axis. Plus mass of the person, 70, times velocity of the person, 0, is equal to mass of the ball, 2, that's 5, times velocity of the ball, 2, that's unknown, plus mass of the person, which is 70, times velocity of the person in photo 2, which is also unknown. But we do know that since the person caught the ball, these two must be equal to each other. So the total momentum on the left side in photo 1 is 5 times 10 I hat. That's 50 I hat, since this term obviously is 0. Is equal to, I'm going to call this velocity over here velocity 2 times 5 plus 70. So this simplifies to 50 I hat equals 75 times V2, and therefore that V2 is equal to 50 divided by 75 is 0.67 I hat meters per second. So this is the velocity of the person just when they catch the ball. Now, the second part of this question was to find out how long it was going to take for this person to come to a stop. It is possible to solve this using forces followed by kinematics, but let's try solving it in a slightly different way. Let's try solving it using impulse. So, in order to solve using impulse, we first need to know how big the friction force is, since the friction force is the thing slowing our character down. If we were to draw the free body diagram of our character at photo 2, there would be a weight force pointing down, a normal force pointing up, and a friction force, a kinetic friction force, pointing left. Now, we can easily solve for all of these quantities. I'm going to set my usual axes. Rightwards is positive, upwards is positive. Weight is equal to mass times gravity. That is a mass of 70 times gravity is 9.81, which works out to 686.7 newtons. Now, this person is not accelerating in the y direction. They aren't collapsing into the ground, and they're not levitating off the ground. So that means that there is no acceleration in y, and therefore that the two forces in y must exactly balance each other out. So if the size of the weight force was 686.7, that means the size of the normal force is also 686.7. That leaves the friction force. the size of friction is given by mu sub k multiplied by the normal force, which is 0.15 times 686.7, which works out to 103.005. I'm just going to call that 103 newtons. So that is now the size of the friction force. Now that we have all this information, we can say how big is the impulse that the friction force is going to exert on our character. We know that impulse is equal to, and this is going to be the analysis from photo 2 to photo 3, we know that impulse is equal to the momentum in photo 3 minus the momentum in photo 2. So, the momentum in photo 3, this person is not moving in photo 3, so the momentum would be 0. Minus, what is the momentum in photo 2? Well, we know that their velocity in photo 2 was 0.67, and the total mass in photo 2 was 75. So, since momentum was conserved between photo 1 and photo 2, you could just easily figure out that the momentum in photo 2 must have also been 50 I hat. Or you could just multiply it out. 75, that's the mass, multiplied by the velocity of 0.67 will also give you 50 I hat. Either way, that's what the momentum was in photo 2. So that works out to negative 50 I hat. That's the impulse. But impulse is also equal to force multiplied by time. And since it's the force of friction that we're worried about, we can say that an impulse of negative 50 I hat is equal to a force of negative 103 I hat newtons multiplied by time. So now it's just a matter of division. The time that it takes for this person to come to a stop is negative 50 divided by negative 103.005 if we're really going to be rigorous about it, which is 0.485, let's call that 0.49. So then, we have used conservation of momentum to compare the velocities of these bodies before the collision to after the collision, find out what the velocity of our character is, and then to figure out how long it takes for this person to come to a stop after the collision takes place. It takes 0.49 seconds, and we were able to solve for that using the free body diagram, finding out how big the friction force is, and applying that to the impulse formulas. Last, let's look at momentum alongside energy. A setup used in ballistics labs is a suspended box that rises when struck by a bullet. Consider this example. A 10 kilogram box is suspended on strings. A 0.05 kilogram bullet is fired into the box. The box rises by 0.15 meters. What is the initial velocity of the bullet before it strikes the box? In this question, a bullet is going to strike a box which is suspended on some strings. Initially, the bullet is moving in this direction, the box is motionless. The bullet strikes and embeds itself in the box, like this, and the box gets pushed backwards. Something like this. So photo 1 is prior to the collision, before the collision. Photo 2 is the time of collision And photo 3 is as the box gets pushed backwards on these strings and rises to its maximum height. Now let's put in all the information we know. The bullet has a mass of 0.05, but its initial velocity is unknown. The box has a mass of 10 kilograms. And after the collision occurs, the box rose by a distance of 0.15 meters. I'm going to set upwards as my y-axis and rightwards as my x-axis. Now we are ready to solve for what was the initial velocity of the bullet. We don't have enough information between photo 1 and photo 2 to solve for the velocity or indeed anything else. We cannot yet apply conservation of momentum between these 2 points. But what we certainly can do is apply conservation of energy between photo 2 and photo 3, because we know how high this rose, so we can figure out what the velocity was over here. Since we know the velocity here, we can then use conservation of momentum to find out what the velocity was of the bullet. So let's try this out. Let us go and examine photo 2 to 3 and specifically apply conservation of energy here. The kinetic energy in photo 2 plus the potential energy in photo 2 plus the work in minus the work out equals the kinetic energy in photo 3 plus the potential energy in photo 3. So let's see what terms we can eliminate. In photo 2, the box is certainly moving, but there's no potential energy because it's at the lowest point. It's along the x-axis. The work in, there is no work in. There isn't anything pushing the box after the bullet has embedded itself inside. There's no work out because we're not bothering with friction. This isn't sliding on a surface. Kinetic energy at 3. The box reaches its highest point over here, which means there is no kinetic energy at all. Potential energy at 3. That means that all of the energy in the box is potential. So that means that this entire conservation of energy statement becomes simply Ke2 equals Pe3. Let's expand this out. Half times the mass in photo 2 times the velocity in photo 2 squared is equal to mass in photo 3 times g times the height in photo 3 squared. Now these two masses are going to be equal to each other. It's the mass of the box plus the mass of the bullet. So we can expand those out and plug in all the information we know. 1/2 times mass of box plus mass of bullet is 10 plus 0.05 times the velocity squared is equal to 10 plus 0.05 times g, which is 9.81, times the height, which is 0.15. Okay, so 10 plus 0.05 gives us 10.05, and then half of that is 5.025. So 5.025 times the velocity squared is equal to 10.05 times 9.81 times 0.15 is 14.79. Now let's divide both sides by 5.025 is 2.943. Which means that the velocity of this combined system in photo 2 is the square root of 2.943, which is 1.72. So that would be the velocity of the box plus the bullet at photo 2. And if we want to be even more specific about this, this is moving horizontally at photo 2. It hasn't yet started to rise. So we could say it's 1.72 in the I hat direction. Now that we are all done with finding out what we can using conservation of energy from photo 2 to photo 3, it's time to turn our attention to conservation of momentum between photo 1 and photo 2. So conservation of momentum says that the total momentum in photo 1 must equal the total momentum in photo 2. Expand that out. The momentum of the bullet, I'm going to label the bullet with a lowercase b in photo 1, plus the momentum of the block, I'll label that with an uppercase b in photo 1, is equal to the momentum of the bullet in photo 2 plus the momentum of the block in photo 2. Now, for lack of space, I'm going to just immediately say that this term over here, that is the momentum of the block in photo 1, is going to cancel. And we know that because initially it's not moving, so it has no momentum. But I'm going to expand out the remaining terms. The mass of the bullet in photo 1 times the velocity of the bullet in photo 1 is equal to mass of the bullet in photo 2, velocity of the bullet in photo 2, plus mass of the block in photo 2 times velocity of the block in photo 2. The mass of the bullet is 0.05. The velocity of the bullet in photo 1 is unknown. But all of that is equal to mass of the bullet in 2, 0.05, times velocity of the bullet in 2. We found out that the combined velocity was 1.72 I hat, plus mass of the block, 10, times velocity of the block, 1.72 I hat as well. Okay, so let us take this 1.72 and multiply it by the total mass, which is 10.05, and that'll give us the total momentum on the right side immediately after the collision. So that gives us 0.05. Velocity of the bullet in photo 1 is equal to 17.24 I hat. Last step, divide this by 0.05 and we get 344.82. So the velocity of the bullet in photo 1 is equal to 344.82 I hat meters per second. This is a classic physics question, where what has happened is we use conservation of energy to solve for the rise of the box between photo 2 and photo 3, and once we have done that, use conservation of momentum to solve for how fast the bullet must actually have been traveling in order to produce this rise in height. In this video, we solved compound conservation of momentum questions, where part of the question required another concept to solve. In the next video, we will look at the final topic in momentum, elastic collisions.